Hello guys, welcome back to a new video. In this video, I'm going to explain section 3 from chapter 3, fluids in motion. Now guys, we have two types of fluids, two types of fluid flows. When a fluid flows, we categorize it into two flows. We say laminar flow or irregular or turbulent flow. Before I explain it, let me give you an example of a laminar flow. Okay, now the video that you saw is an example of a laminar flow. A laminar flow, guys, is a smooth and a non-messy flow. You see that the oil was pouring into the container very smoothly without any turbulences, without any messiness. This is called laminar flow, guys. Irregular or turbulent flow is opposite to that, okay? It is messy, the water or the fluid flow is splashy, like it has many eddies due to the obstacles that are in this fluid. So that's why it can disturb the flow of the fluid. We have two types, laminar flow and irregular or turbulent flow. You have idle fluids, guys. Idle fluids, they have no internal friction, okay? Or you can just say that they have no viscosity, okay? And they are incompressible. This is an idle fluid. We're going to talk about the properties of them in just a minute. Viscosity, guys, is just the amount of resistance or the internal friction of a fluid, okay? If you have water and syrup, you see that the syrup flows very, very slower than water. Why is that? This is because of the high viscosity of syrup. Or oil and water. Okay, oil has a much has a higher viscosity, and that is why it's used in cars to decrease the friction between the components of the car. But water flows much faster due to its low viscosity. And it is due to the molecular structure of both of these substances. You have the properties of idle fluids. We said idle fluids, they have no internal friction or no viscosity, and they are incompressible. These are the properties of idle fluids. No internal friction, incompressible, and they have a steady flow, meaning that density, velocity, and pressure are the same at every point. And you have non-turbulent, okay? Basically, if it's steady, if it has a steady flow, it means that it's non-turbulent. Guys, you have principle of continuity, or the equation of continuity. It says that the mass that enters the system is equal to the mass that leaves the system. And we have an equation for that. Let's prove that equation first, and then I'll come back to the book later. Now look, we have M1, which is equal to M2. The mass that enters the system is equal to the mass that leaves the system. And you remember, guys, we said that density is equal to mass over volume. And to find mass, I'm going to say mass is equal to density multiplied by volume. I can write, instead of M1, I can write density 1 multiplied by volume 1 is equal to density 2, sorry. This is the second part, and volume 2. And now, guys, you remember that we said volume is equal to length times width times height. And we said because this is area, length multiplied by width is called area, I can just say that volume is equal to area multiplied by height. Here, guys, for the continuity equation, I'm just going to write this one as delta x, okay? It's the same thing. Now, instead of writing volume, I can say rho 1, which is density, multiplied by area 1, multiplied by delta x1, okay, which is equal to rho 2 multiplied by area 2 multiplied by delta x2, okay? This is what, guys, this is delta x, sorry, this is delta x2. Now, guys, we studied another equation in the first chapter. If you remember, we said that velocity is equal to delta x divided by delta t, okay? To find delta x, I can say delta x is equal to velocity multiplied by time. So instead of writing delta x here, I'm just going to simply write velocity multiplied by time. Okay, let's do that. So you have P1, sorry, I always say P1, this is row 1, multiplied by area 1, multiplied by delta x1, but instead of writing delta x, I will say V2, which is velocity this time, V1, multiplied by delta T1, which is equal to row 2, multiplied by area 2, and then you have delta x2. You can just write velocity 2 multiplied by delta T2. Now, guys, the time interval is the same, so they're going to cancel each other. And also, the fluid does not change. Okay, so density is also the same. So you have the final equation, which is equal to A1 multiplied by V1 is equal to A2 multiplied by V2. This is called the continuity equation, meaning the mass that enters a system is equal to the mass that leaves, the mass of a fluid, of course, is equal to the mass that leaves the system. And this is the proof here, if you want to write this down. Because mass is conserved, so we know that the mass flowing into the bottom of the pipe must equal the mass flowing out of the pipe, the top of the pipe. Now, guys, if you are trying, for example, to water your plants, okay, you see that there are some plants that you cannot reach them. So you just basically what? You, for example, are going to decrease, or you are going to pinch the hose, and it's going to flow much faster, okay? So that the water reaches the plants that you cannot reach them, okay? So you have decreased the cross-sectional area so that the water flows faster, okay? But careful, okay? This might seem, most people have a misconception about this one. They think that if you decrease the cross-sectional area of a hose or of a pipe, then it's going to have a higher flow rate. Flow rate is different than the velocity of the fluid. Careful. Flow rate never changes. Okay, it's the amount of water that leaves the pipe, that leaves the hose. It never changes. Okay, it's only the velocity at which the fluid is flowing. By the way, flow rate is area multiplied by velocity, which has a unit of volume divided by time. Meter cubed divided by second. Okay, we're going to use this equation careful. We will say flow rate is equal to volume divided by delta T, or flow rate, you remember, is equal to a area V1, which is equal to V divided by delta T, and it has a unit of meter cubed per second. Okay, the volume the volume of the water divided by the time interval. Now, guys, we have Bernoulli's principle. The pressure decreases as the fluid's velocity increases. Okay, so you have this one, for example, here. Here it has a very high pressure and the speed of the fluid is really low. But if you decrease the cross-sectional area as we just talked about it, it's going to have a higher speed, a higher velocity, and it's going to have a lower pressure. Okay, meaning the water is going to flow faster, but the pressure is going to be much lower. Okay, it's like saying there's a room full of people. If people are flowing if people are leaving the room very slowly, then it's going to be having a high pressure. Okay, but if people are moving faster and leaving the room much faster, then it's going to have a lower pressure and it's going to have a higher speed too. So if you have low pressure, if you have a higher speed, it means you'll be having a higher speed too. Let's explain this phenomenon. How can a lift on an airplane be explained in terms of Bernoulli's principle? Okay, so you have this, guys. This is, let's say, the wing of an airplane. How is Bernoulli's principle can be applied to this one? How can it be applied to this one? Guys, basically, okay, the design of the airplane is made like this. So it's going to have what? Of course, you have air, and air is a fluid. The velocity above the wing, is going to be very, very high, okay? The velocity here, V, is going to be very high. And the pressure is going to be, we said that if you have a high velocity, then pressure is going to be what? Pressure is going to decrease. So pressure is going to be decreasing here. This is above the wing, but beneath the wing, guys, the downside, it's going to have what? It is going to have a smaller, or it's going to have a lower speed, okay? But the pressure here, we said that if the speed is decreasing, then pressure is going to increase too. This difference in pressure, guys, as you see here, this difference in pressure is going to what? Is going to exert an upward force on the wing of the airplane, and that is how it's going to raise the airplane, okay? It is due to the pressure that is high beneath the wing and the velocity that is low beneath the wing. Now, guys, we have these equations. Try to memorize them as you will be using them a lot in this chapter. You have Bernoulli's equation, which relates to a fluid moving. You have pressure plus 1 over 2 rho velocity squared plus rho gh, which is equal to a constant. If you are comparing 2 points, let's say you have 2 points, point 1 and point 2, you're going to use this equation, P1 plus 1 over 2 rho velocity v1 squared plus rho gh1. This is the height, and the first height, by the way. Then you have P2 plus 1 over 2 rho v2 squared plus rho gh2. This is the second height, okay? If the fluid is not moving, guys, careful, if the fluid is not moving, so we're going to what? We're going to cancel the ones that have velocity in them. For example, if the fluid is not moving, then we say it's static. Static means not moving. If the fluid is not moving, then it has no velocity. So this is V1. Yes, we have V1. It's going to be 0. And this is V2. This one is also going to be 0. So you have P1 left plus. This is also going to be 0 because you only have H2. H2 is the height here, is the height of the container. Or for example, you have a tank, okay? H2 is going to be the height of the tank. So you have P1, which is equal to P2 plus rho gh2. This is what? This is going to be the equation used for a static fluid. If it's a horizontal pipe, this time the pipe is like this, okay? It's horizontal. It doesn't have a height, okay? There is no height, okay? There is no height. You're going to say that the ones that have height this time, look, it's still this equation that you're using, but in different ways. So it says if it's horizontal, it means that h is going to be 0, height. Then this one is going to be 0, and this one is going to be 0 too. What do you have left? You have P1 plus 1 over 2 rho V1 squared is equal to P2 plus 1 over 2 rho V2 squared. This is the horizontal pipe. Try to memorize these equations because you will be needing them in solving the practice questions. You have another equation, guys, which is used for finding the velocity at which the most of the time you are going to be given a tank, and it has an opening where the fluid is leaving the tank, here. It says find the velocity or the speed at which the fluid is leaving the pipe. You're going to say V1 is equal to square root of 2g h2 minus h1. This h2 minus h1, guys, you're going to be always given in the question. You don't have to say subtracted or I have h2 and h1. It's going to directly give you this one. Okay, for example, this is equal to 0.5 meter. So all of this is equal to 0.5 meter. This is really an important equation. In the next video, I'm going to explain how can you get this equation too. But in most cases, you are going to use this equation. You don't have to know how to rearrange the equation and then get this final equation. See you in the next video.